Good afternoon, sir.
Good afternoon. Okay, so right now we will continue our discussion with the subtraction with the tens complement. So we are going to just take another example where the minuend is 3250 and the subtrahend is 7253. And for convenience, what we will do, we will make the number of digits equal in both the subtrahend and minuend. So that is why I will put 0 in the leftmost position. So right now the number of digits present in both the minuend and subtrahend are 5. So what I will do, I will go for m minus n using tens complement. And you need to understand here, from here, that is here m less than n. The minuend is less than subtrahend because minuend is 3250, subtrahend is 7532. So the process of the subtraction is same. So first we have to find out the tens complement of subtrahend n, and how to obtain the tens complement of capital N. First you have to subtract each and every digit present in subtrahend from 9. So 72532, then you have 76472, and then you will add 1. So you have 27468. So this is the tens complement of n. And now what you have to do, you have to add minuend, that is 3250 and 0 over here, and tens complement of n, which is 27468. You just add these two. You have 8, 1, then 7, then 0, then 3. Okay? So if you see this added result, how many digits present over here? 5. And also both in minuend and subtrahend, how many digits are present? 5. So in this particular case, no end carry, because already we have m less than n, the minuend less than subtrahend. That is why no end carry has been generated. So for the m less than n, means when minuend less than subtrahend, your results should be, or the sign of the result should be negative, right? So how to represent it? The final result is equal to minus tens complement of 30718, tens complement of the added result. Okay, and you have to put minus sign in front of that. So minus, what is the tens complement? It is 2, then it is 8, then 2, then 9 and 6. 69,208. Right? Now, if you do it conventionally, where m is equal to 3250 and n is equal to 72532, and you have to do the minus. So what you will do? You actually do in this manner, m minus n. So the result will be, you put minus sign in front of, and you are actually subtracting the lower value from the higher. So in this way, you are also getting the 69,282 and minus sign in front of that. So just tell me, do you have any doubt? I understand that in the conventional process you don't have any doubt, but in case of tens complement, do you have any doubt? Is that okay with you?
Yes, sir.
Okay. Now we will talk about the subtraction operation using the twos complement. Right now we have a x which is 10101000, and we have a y which is 10000011. So you have to find out x minus y using twos complement. So the process is similar. So first you have to find the twos complement of y, and it is nothing but, first you will go for ones complement, which is 0 1 1 1 1 0 0, and then you will add 1. So you have 1 0 1 1 1 1 0. So this is the twos complement of y. And then what you have to do? You have x, which is 10101000, and then you have twos complement of y, which is 0 1 1 1 1 0 1. So what you will do? You will just add these two. You have 1 0, then you have 0, then you have again 0, then you have 1, then you have 0, then 0, then 1. So if you see how many bits present in the x and y, you just check it out. How many bits present here? 1 2 3 4 5 6 7. How many bits present in y? 1 2 3 4 5 6 7. So n is equal to 7. But how many bits present in this result? 1 2 3 4 5 6 7 8. So this is actually your end carry. So when end carry generated, it means x greater is equal to y. Now the same process you will follow to remove that end carry. In case of yes, in case of tens complement, we again had an end carry, because the minuend greater than subtrahend. So how to remove that end carry? Subtract r to the power n to remove the end carry. And what we have done, you see, we have to subtract r to the power n from r to the power n minus n plus m to remove the end carry, because this actually gives you the this is the subtraction operation we are doing in the r's complement method. Because in the r's complement method, what we are doing, we are actually taking the r's complement of the subtrahend, and then we are adding the minuend to the r's complement of the subtrahend. Okay, means okay. Again, I want to clear one thing, that when we are working with the pen and paper, then we are following the conventional procedure to find out the subtraction. Okay, so there will be no problem with the conventional process, right, when we are using the pen and paper. But in case of digital computers, okay, we are using this complement method. Why? Because we know when the minuend will be less than the subtrahend, we need to borrow from the next higher position, okay, when we will go for the subtraction. So instead of doing subtraction, we are actually doing addition with the r's complement of the subtrahend. So in this case, we can easily eliminate the concept of borrowing, right? When we are adding, then we don't need to borrow from the next higher position if the subtrahend is greater than the minuend. When it is on the pen and paper, then there is no problem. But when it is when we are dealing with digital computers, the problem of borrowing from the next higher position will be eliminated if we use this complement method. So you just remember, in the complement method, when we are doing the subtraction, actually what we are doing, we are actually doing the addition. How? First, I am obtaining the r's complement of the subtrahend, and then we are adding the minuend to the r's complement of the subtrahend. So this gives you the difference, right? So in the complement technique, actually you don't need to do the subtraction in true sense. You are actually doing the addition to eliminate the complexity associated with the borrowing process. So what is the process? First, you have to find out the r's complement of the subtrahend. Then you will add the minuend to the r's complement of the subtrahend. That gives you the value of actual difference. So but you are not doing the subtraction in true sense in case of digital computers. Okay. So now, what was our main topic? The topic, how to remove the end carry. So in case of tens complement technique, what we have seen, when end carry generated, means when m greater than n or minuend greater than subtrahend, to remove the end carry, we have to subtract r to the power n from this added result. Okay, so you see, we have to subtract r to the power n from r to the power small n minus capital N plus capital M to remove the end carry. So the same process will be followed in this case also. Here you see you have an end carry. So in case of 2's complement method, when we have an end carry, it means x greater is equal to y, then we need to subtract r to the power n, that is 2 to the power n, from r to the power n minus n plus n, or you can easily say 2 to the power n minus y plus x. Okay. So now what is the value? 1 0 0 1 0 0 0 1. Okay. Now, how many bits were there? N is equal to 7 bits were there. So you have to subtract r to the power n, means 2 to the power 7 you have to subtract. So what is actually 2 to the power 7? It is 1 followed by 7 zeros, and you do the subtraction, you have 1 0 0 0 1, then again 0 0 0. So this is the actual value of the difference. Okay. Now what we had, if we follow the conventional technique, you also know the conventional technique of binary subtraction. So when we have x, what it is 1 0 1 0 1 0 0, and we have y 1 0 0 0 0 1 1. So if you just do the conventional subtraction technique, binary conventional subtraction technique, so you see, if you just carefully observe, here you have to subtract 1 from 0, so there is a process of borrowing from the next higher position. So the difference will be 1 and the borrow will be 1. So you have 0, then you have 1, then 0, then 1 0 0. Okay. One. Oh. Oh no. I think 1 minute. I have done some mistake. I think here will be 0 over here. Okay.
Yes, sir.
0 will be here due to the borrowing. Okay, I have done some mistake. So this is the conventional way of doing the binary subtraction. And you see here the borrowing process involved. So, but in the previous case, when we are using the 2's complement method to do the subtraction, actually the complexity associated with the borrowing process is actually eliminated, because we are not doing subtraction in the true sense. We are actually doing the addition. Okay, so that is why we are using this 2's complement method of subtraction in the digital computers. Okay. So right now, okay, this is the one technique, and another example is where x is equal to 1 0 0 0 0 1 1 and y is equal to 1 0 1 0 1 0 0. So then you have to do the x minus y using two's complement method. So what you have to do, you just find out the two's complement of y. And it is nothing but how much? 0 1 0 1 0 1 1. Then you just add 1 over here. So you have 0, then 0, then 1, then 1 0 1. Now what you will do? You have x, which is 1 0 0 0 0 1 1, and you have 2's complement of y, which is 0 1 0 1 1 0 0. So we will do the addition. You have 1 1 1, then 1, then 0, then 1. Okay. Now what is the observation? The observation is very simple. You see how many bits present in the x and y. 1 2 3 4 5 6 7. Here also 1 2 3 4 5 6 7. And in the added result 1 2 3 4 5 6 7. So actually what? There is no end carry. So when there is no end carry, it means x less than y. And when x less than y means when minuend less than subtrahend, it means the sign will be changed. So you have to put a negative sign in front of a result. So the final result will be negative sign, and it will be two's complement of this added result, which is 1 1 0 1 1, 1, 1. So I think you have minus, you have 0, 0, 1, 0, 0, 1, then 0, 0, 0, then again 1. So this is the original difference, actual difference, right? Okay. So in this case, you don't have any end carry. That is why x less than y means you have to put the negative sign in front of your final result. Okay. The same thing we have done in case of tens complement also. When the minuend less than subtrahend, we have put the negative sign in front of the result, and in bracket there was the tens complement of the this added result. Okay. So the result will be in the complemented form. Okay. So right now we will discuss about the subtraction using r minus 1's complement. Okay. So right now, again we will take one example where x is equal to 1 0 1 0 1 0 0 and y is equal to 1 0 0 0 0 1 1. So we have to find out this difference using 1's complement. So how to do that? The process is very simple. First you have to write this x 1 0 1 0 1 0 0. Then you will write the 1's complement of y, and what it is? 0 1 1 1 1 0 0. Then do the addition. You have 0 0 1 1 0, then 0, then 1, then 0, then 0, then 1. So if you check the number of bits present in x and y, it is 1 2 3 4 5 6 7. It is also 1 2 3 4 5 6 7. So 7 bits present in x and y. But in this added result, how many bits are there? 1 2 3 4 5 6 7 8. So this is actually your end carry. So when end carry generated, it means x greater than y. Now here the process is little bit different to remove this end carry. In the last case, how could we remove the end carry? We just subtract r to the power n. So the small n, the value of small n was 7 and the base r is actually 2. So we have subtracted 2 to the power 7 from this result. But here, if you just consider the r's complement and r minus 1's complement, what is the formula to find out the r's complement? R to the power small n minus capital N. And what is the formula to find out r minus 1's complement? R to the power n minus n minus 1. So what is the difference? The difference is r minus 1's complement. Okay. The difference colon r minus 1's complement is 1 less than the r's complement. Isn't it? R minus 1's complement is 1 less than the r's complement. And this same thing is actually what we can say, it is the same thing actually followed in the subtraction operation also. Okay, so this difference in values, what is the difference? The difference is 1. So the r minus 1's complement is 1 less than the r's complement. This same difference will be carried out in subtraction operation also. So when you are using the R's complement, or let us say when you are using the 2's complement method for subtraction, so whatever value you will obtain, if you use the R minus 1's complement, that is 1's complement, the difference is actually 1 less than the actual value. Okay. So for the, okay, I will write for 2's complement method. And for the one's complement method, right? So here the difference is 1 less than the actual value. Okay. And here the difference is identical with actual value. Okay. So in the 2's complement, means if we see this thing, okay, if we see okay, if we see this example, here we have done the difference x minus y using 2's complement, and after doing all the procedure, we are actually obtaining 0, 0, 0, 1, 0, 0, 1. This is the actual value of the difference, and it has been verified from the conventional technique. The difference, the actual value of the difference is 0, 0, 1, 0, 0, 1. Okay, but in case of 1's complement, what will happen? The difference, what you will get, that will be 1 less than the actual value. Okay, are you getting my point? What I'm trying to say? Yes or no? Tell me. Right. So whatever difference you will obtain from the 1's complement method, that will be 1 less than the actual value. So in this case, what will happen when you will have an end carry? How could you remove it? So you will just do, you will replace, you will take the end carry and place this end carry towards the extreme right position, and then you will add, because actually this value is 1 less than the actual value. So you will take this end carry and you will place this end carry at the rightmost position, and then you will add. So you have 1, then 0, 0, 0, 1, 0, 0. Okay, so this is the difference, actual difference. Okay, so if we just again write 2's complement, and here it is 1's complement, and in both the cases x greater is equal to y, means minuend is greater than subtrahend. So here x is equal to 1, 0, 1, 0, 1, 0, 0, y is equal to 1, 0, 0, 0, 0, 1, 1. Here also x is equal to 1, 0, 1, 0, 1, 0, 0, and y is equal to 1, 0, 0, 0, 0, 1, 1. So here we will write x is equal to 1, 0, 1, 0, 1, 0, 0, and 2's complement of y, which is actually 0, 1, 1, 1, 1, 0, 1. Now you will add these two, 1, 0, 0, 0, 1, 0, 0, 1. And in this case, you will write x 1, 0, 1, 0, 1, 0, 0, and you will write 1's complement of y, which is 0, 1, 1, 1, 1, 0, 0. And again, you will do the addition operation, 0, 0, 0, then 0, then 1, then 0, 0, then 1. Okay. So in both the cases, if you observe very carefully, you have the end carry. This is the end carry. This is also the end carry. Now, in case of 2's complement, how to remove end carry? You have to subtract to remove end carry. Subtract r to the power n. And for this particular case, this is actually 2 to the power 7, because the binary in binary system r is equal to 2, and how many digits are there, bits are there? 1, 2, 3, 4, 5, 6, 7. 2 to the power 7. So what we will do, 2 to the power 7 means 1 followed by 7 zeros and do the subtraction. So what you have? 1, 0, 0, 0, 1, 0, 0, 0. So this is the actual difference. Now in this case, what we know? When we are doing subtraction operation using the 1's complement, the difference we are getting, that is 1 less than the actual difference. So how to rectify it? So and this actually happens when you have an end carry. Okay, so I will write here. In r minus 1's complement, the difference is 1 less than the actual value when there is an end carry. Okay, so then how to rectify this thing? You will take that end carry and place the end carry at the extreme right, and then you will add these two. So you have 1, then 0, 0, 0, 1, then 0, 0. So this is the actual difference. So this is the difference between the subtraction process using 2's complement and using 1's complement when x greater equal to y. Okay, now the another case will be there when x less than y. So for x less than y, the procedure is same. So 2's complement when x less than y, and 1's complement when x less than y. Now here x is equal to 1, 0, 0, 0, 0, 1, 1, and y is equal to 1, 0, 1, 0, 1, sorry, 1, 0, 1, 0, 0. Here also x is equal to 1, 0, 0, 0, 0, 1, 1, and y is equal to 1, 0, 1, 0, 1, 0, 0. So you will write x over here, 1, 0, 0, 0, 0, 1, 1, and 2's complement of y. How much it is? It is 0, 1, then 0, 1, then 0, 1, 1, right? And if you put 0, 1, 1 and then add 1, 0, 0, 1, I think 1, 0, 0. Is that correct? You have 1, 0, 1, 0, 1, 0, 0, then 0, 1, 0, 1, 0, 1, 1 plus 1. So 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0. Yes, 0, 1, 0, 1, 1, 0. The same thing happened over here. 1, 0, 0, 0, 0, 1, 1. That is 0, 1, 0, 1, 1, 0. Now what you will do? You will add, after addition, what you have? 1, 1, 1, 1, 0, 1, 1. Again here, 1, 1, 1, 1, 0, 1. And if you check very carefully, there is no end carry because the added result has also the 7 bits. And also the minuend and subtrahend have 7 bits. So no end carry. So when no end carry, it means x less than y. So what you have to do? You have to put the negative sign in front of your result. So how could you represent it? Negative sign, and then again 2's complement of 1, 1, 0, 1, 1, 1, 1. And you see here also no end carry, means x less than y. So the result will be, you have to put negative sign because minuend is less than subtrahend. So automatically a negative sign will come. Put negative sign and you have to write, you have to represent in the complement form. So first 1's complement of 1, 1, 0, 1, 1, 1. So the process is same. Okay, so for 2's complement, you have to write negative sign and then 2's complement of the result, additive result. And for the 1's complement, you have to put negative sign and then you have to represent in the represent the additive result in the 1's complement form. Okay, so finally, you have minus 0, 0, 1, then 0, 0, 0, 1, and here also you have minus 0, 0, 1, okay, I have done something mistake over here. It should be 1, 0, 1, 0, 1, 0, 0, right? So 0, 1, 0, 1, 0, 1, 1. Okay, so this value will be changed little bit. It is 0, then it is 1, then it is 1, then 1, then 0, then 1. So 111, 0. So the 1's complement is 0, 0, 1, 0, 0, 0, 1. You see, both the results are same. Okay, so these are all about the subtraction operation, right? Do you have any doubt? Is that okay?
No, sir.
Okay. Now we will start the signed binary number. So in ordinary arithmetic, a negative number is indicated by a minus sign and positive number indicated by a plus sign. All we know this thing. Because of the hardware limitations, computers must represent everything with binary digits, referred to as bits. It is customary to represent a sign with a bit placed in leftmost position of the number. So what is happening when we are doing the arithmetic operation in pen and paper? So we are actually putting the plus or minus sign in front of the number. If you have a minus sign, then you will put the minus sign. If you have a plus sign, then maybe you can put a plus sign, or you don't need to put any sign. So automatically it will be considered as the plus sign. But when in case of digital computers, the computer also considered the signs, whether it is positive or negative, as bits, as binary bits. Computer cannot work with plus sign or minus sign. It can work with only binary bits, either 0 or 1. So in that case, you have to represent the plus or minus sign with bits also. And the sign bit will be placed at the leftmost position of the number. That is written. So for the plus sign, we will always use 0, and for the minus sign, we will always use 1. And this sign bit will be placed at the extreme left of the number. Okay? Now it is important that both signed and unsigned binary numbers consist of a string of bits when represented in a computer. The user determines whether the number is signed or unsigned. If the binary number is signed, then the leftmost bit represents the sign and the rest of the bits represent the number. Okay. So it can be represented, okay, suppose you have a number 01001. Now the leftmost position already indicated. Actually at the leftmost position, the 0 is over there. And that 0 defines a positive sign. Or generally we can say this bit, this extreme leftmost bit is actually defines the sign. And because there is a 0, it will be a positive sign. And the rest of the bits, which is 1001, is actually represents the value, and the value is 9. So finally, from 01001, we can say it is a plus 9. Okay. If the binary number is signed, then the leftmost bit represent the sign and rest of the bits represent the number. If the binary number is assumed to be unsigned, then the leftmost bit is the most significant bit of the number. Most significant bit means it has the greater numerical value. The least significant bit means it has lowest numerical value. Okay. Okay, if we take this 110101, so this will be MSB. The greater numerical value. So what is the equivalent of this one? It should be 1 into 0, 1, 2, 3, 4, 5. So the equivalent value is 32. And for this one, it is the least significant bit. So it is actually what? 1 into 2 to the power 0, that is 1. So low numerical value, less numerical value. So that is why this is the LSB and MSB. So what we are doing, we are actually putting the sign bit at the leftmost position. So for example, the string of bits 01001 can be considered as 9 for unsigned binary or a plus 9 for signed binary, because the leftmost bit is 0. Okay. So again, I will show you. So suppose actually 9 can be represented by 1001. Now, what is the 5-bit representation? That is 1001, and you can put 0 at the extreme leftmost position. So this is the 5-bit representation of 9. So this is what left most position, and this bit defines sign, and this or you can say defines value. So 01001. So 01001 can be represented as simple 9 for an unsigned binary system, or 01001 can be represented as +9 for the signed binary system. Now, this leftmost position, this 0 at the leftmost position is actually representing this plus sign. Okay. Now the string of bits 11001. Okay. Now we have 9. We had 9, which was 1001. Now in the previous case, at the leftmost position, we had 0. So it can be treated as 9, or it can be treated as +9 in the unsigned binary. And this is in the signed binary number. But now we have 1001, and we are changing this 0 bit into 1. So what we can have, we have 25 for unsigned binary. How? Because if you just calculate the coefficients, you have A0, A1, A2, A3, A4. So 1 into 2 to the power 4 plus 1 into 2 cube plus 0 into 2 to the power 2 square plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. You have 16 plus 8 plus 1. So which is 25. So 25 for unsigned binary. But in case of signed binary, you have -9. Because if you will consider 1, then 1001. So this is the leftmost bit, and this defines the sign. And we know when we have 1 at the leftmost position, it defines the negative sign, and the rest of the bits defines value, which is actually 9. So in signed binary system, 1 1 0 0 1 actually gives you minus 9. Okay, any doubt?
No, sir.
Clear? Okay. Now the representation of the signed numbers in the last example is referred to as the signed magnitude convention. So whatever we have discussed till now in the signed binary system, it is the signed magnitude convention. The leftmost bit is represent the sign and the rest of the bit represent the value. So this is the signed magnitude convention. This is the representation of the signed numbers in the ordinary arithmetic. Now, signed complement system uses either ones or twos complement, but twos complement, okay. When arithmetic operation is implemented in a computer, it is more convenient to use a different system for representing negative numbers referred to as the signed complement system. Here also we will use the complement to represent the sign. Till now, whatever we have discussed, that is the signed magnitude system, but in case of digital computers, it is more convenient to use the signed complement system for the negative numbers, not the signed magnitude. We will use the signed complement system for the negative numbers in the digital computers. In this system, a negative number is indicated by its complement. Since positive number always start with 0 in the leftmost position, the complement is always start with a 1, indicating the negative number. Okay, means what? In case of plus 9, it will start with 0. 0 will present at the leftmost position, and then you have the value. Okay, for the signed complement system, when we are representing the minus 9, what I will do, I will complement this part, means the complement of 1001 is 0 110, and also I will take the complement of the sign bit also. So this will be 1. So right now you can observe at the leftmost position 1 is present. So it means this actually a negative number. So that is why you see, since the positive number always start with 0 in the leftmost position, the complement is always start with a 1, indicating the negative number. That is why we can represent the negative number with complement. The signed complement system uses either ones or twos complement, but the twos complement is most common. Now consider the number 9 represented in binary with 8 bits. Right now, previously we had represented 9 with 5 bits. So when we are representing the 9 with 5 bits, we had 1 0 0 1, and we are putting 0 in front of 1001, or you can say you are actually putting 0 at the extreme leftmost position, and this is the 5-bit representation. Now the same 9 can be represented by 8-bit. How could you do that? You have 1001, and you just put 4 zeros in front of 1001. So this is the eight-bit representation. Okay. Now plus 9 is represented by a sign bit 0 in the leftmost position, followed by the binary equivalent of 9 to give 0 0 0 0 1 0 0 1. Already I have represented it. Now this at the leftmost position there is a 0, so 0 will be represented this plus sign. And okay, there is only one way to represent +9, but there is 3 different way to represent -9 with 8 bits. So what are the ways? Just give me one moment. Signed magnitude representation, where the leftmost bit 0 will be changed to 1 and rest will be intact. Signed 1's complement, where all the bits including the signed bit will be 1's complement. And for the signed 2's complement representation, there all bits including the signed bit will be 2's complement. But for the positive number, the representation process will be identical for these 3 methods. So for signed magnitude representation, signed 1's complement representation, and signed 2's complement representation, the positive numbers are same. The representation of the positive number is identical for these 3 methods, but the representation of the negative number is different for these 3 methods. So we will continue on this continue discussion on this topic in the next class. So today I am going to conclude this class. Please send the attendances, and I will share the slide today by today.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Sir, also kindly update the SAP portal, na?
Hmm.
Yes, sir. Thank you, sir. Have a great day, sir.